To put it simply, 2D motion is like analyzing two separate 1D motions using vector decomposition. Instead of analyzing the x and y-axis motions separately after drawing two graphs, we solve them by analyzing them simultaneously since they share the same time. Since the time is the same, we solve them simultaneously, okay? Hello, this is Minsicom from Minsicom Academy. Today we're going to cover the concept of two-dimensional motion. You can think of this as adding the concepts of projectile motion and circular motion. The first chapter is on projectile motion. Projectile motion is generally this kind of motion. So this isn't a simple linear motion where an object moves along a single straight line. Instead, projectile motion is fundamentally about simultaneous movement in two dimensions. It's the kind of motion where an object is moving along the x-axis and the y-axis at the same time. Generally, the one-dimensional motion we've done so far has been solved as x-axis motion or y-axis motion when gravity acts on the y-axis. So, how did we solve x-axis motion, for example? After knowing the acceleration, from the AT graph, if we know the acceleration, that's a zeroth order function. This integrates to a first-order linear VT graph and then to a second-order quadratic ST graph. That's how we analyze them. Then, as an additional step when solving problems is, what does this area represent again? If we look at the motion up to some time t0, this area gives us the change in velocity, delta v. And what does the area in this graph represent? This one gives us the change in position, delta s, right? We call this the displacement, delta s, and that's how we've derived formulas and solved problems up until now. However, in projectile motion, movement occurs along both the x and y axes simultaneously. We've been solving problems with just one axis, but now there are two. That's exactly why it's called two-dimensional motion. Then, for example, let's consider it a ball. Consider a ball thrown diagonally at an angle theta. It rises, pauses for an instant at the very top, and then begins to fall as its vertical velocity turns negative. This entire path is what we call projectile motion, and attempting to analyze it all at once is a complex task. So, because it's difficult to analyze everything simultaneously, we use a method called vector decomposition. All right, here's the solution for 2D motion. Use this and you'll solve them all. Simply put, if it's 2D motion, you can solve it all. First, in the method for solving 2D motion, we take the initial velocity of the ball, v0. Then the first step is to decompose the velocity vector. Decomposing a vector means splitting it into velocities along the x-axis and y-axis, splitting it into v sub x and v sub y. Got it? To decompose the vector, you need to know the angle, right? Angle. Because the initial velocity of projectile motion is actually, it's the sum of the vectors v sub x and v sub y. Do you understand? This v0 is, the screen keeps moving. The v sub x vector with the I unit vector and the v sub y vector with the j unit vector. At this point, you can write it like this. It's the sum of these vectors. Do you understand? We first decompose it like this. Then, if cosine theta is indicated here, Vx can be calculated like this. Vx is calculated as v0 cosine theta. Got it? This vector v0 cosine theta, because cosine is adjacent over the hypotenuse, then Vg is calculated like this. It's calculated as v0 sine theta. After vector decomposition, the second step is to find the acceleration and then draw the graph on the x-axis and y-axis. So, after finding the acceleration, x-axis motion, this is what's coming up. You can draw two graphs for the x-axis motion and y-axis motion. then the method to solve it is the same as one-dimensional motion, you know? After finding the acceleration, draw the x-axis and y-axis graphs separately. Got it? In this case, like this. Now, when a ball is thrown, how is it solved? I'll erase this and explain a bit. Now, if we draw each one, let's say we found v sub x and v sub y, then the value v sub x is v sub 0 cosine of theta, and v sub y is found as v sub 0 sine of theta. Then now we draw two graphs, the x-axis graph and the y-axis graph, like this. Since it's a two-dimensional motion, you can think of interpreting it as two one-dimensional motions, which makes it a two-dimensional motion. Until now, we've completed it by drawing one graph for linear motion, but this involves x-axis movement, meaning the ball is moving along the x-axis. This is x-axis motion. Movement along the x-axis. Then there's the up and down movement, right? That's the y-axis movement. Y-axis movement. By dividing it into two like this, you can draw it separately with graphs like this. This kind of graph, that kind of graph. After drawing them separately, you interpret them simultaneously. Got it? If you draw the two graphs separately first, one by one, it's a bit easier. Then interpret them simultaneously. Third, pick an arbitrary time, t0, and analyze both motions at that instant. Because even if it moves separately along the x-axis and y-axis, the time for the ball will flow the same, right? Then let's try drawing it first. Now, the only acceleration the ball is experiencing is gravitational acceleration, right? When you throw the ball, for example, a ball in projectile motion. Then there is no acceleration time graph on the x-axis. Right? There is no acceleration here. Currently, no acceleration is acting on the object. So, how does the vt graph look? It becomes a constant function with v, as mentioned before, v0 cosine of theta, like this. Do you understand? Then if this is 0, how does the st graph? This becomes a linear function like this. So, look at this. Let's call this change delta s with an initial position s0. Let's say this is an arbitrary time t0. If it's an arbitrary t0, what about this height? The displacement becomes delta s sub x, which is the distance moved along the x-axis at time t0. And how about the y-axis? The y-axis has gravitational acceleration g, right? It's being acted upon by gravitational acceleration g downward, so it goes up, stops, and then comes back down. That's the motion on the y-axis. Then how do you draw the at graph for the y-axis? You draw it as negative 9.8 like this. Okay, then how does the vt graph look? Since this is a negative linear function, the initial velocity was upward. It would just be like this from the initial velocity, right? It was the initial velocity intercept, v0 sine of theta. The intercept is vy, right? So this is it. Then how about the third one, st? It's concave down. Since it's negative, it's concave down. The slope is 0 right when the velocity is 0 at the peak. Then it goes down. It looks like a projectile motion like this. Then if this time is t0, I set the time t0 over here earlier. Here. Then this value should also be set as t0. This value is the same. I changed it to this blue t0 and black t0, but time flows the same. Got it? The ball can't be in two places at the same time, so you can solve the problem by making this t0 the same. Interpret simultaneously. If you do this, you can absolutely crush any problem you face. Okay, to explain simply, in one-dimensional motion, because of vector decomposition, two-dimensional motion is like drawing two one-dimensional motions. By decomposing and analyzing the vectors, you separate them into x-axis motion and y-axis motion, and instead of drawing two graphs and analyzing them separately, since the time is the same, you solve it by interpreting simultaneously. Now let's reinforce this by solving a problem with an example. Now, if you solve it like this, you can solve all the problems. So I've prepared an example, let's read it and solve it. So, a cannon fires a projectile at an angle of 60 degrees with the x-axis. At time t0, it went 280 meters along the x-axis, and when it reached a total of 560 meters, The projectile fell back to the ground, so it means the projectile was at its peak at 280 meters along the x-axis and then fell down. Got it? Now let's assume the cannon's height can be ignored and solve the problem. While the cannon has some height, it's less than 1 meter, so we'll ignore it, because the total distance is 560 meters, right? So, A, what is the value of t0? At first, students might not know how to solve this, but don't panic. You must always find the acceleration. But in two-dimensional motion, instead of finding the acceleration right away, you should first separate x and y, and then find the acceleration for each axis. Now, I'll show you how I do it. If the shell is like this, they didn't tell us the initial velocity. Since it wasn't given, we should insert an arbitrary value for v0, but this was given as 60 degrees. So now split by Vx here, then Vx is cosine 60, so how much is it? It would be 1/2, right? Then it becomes 1/2 times V0, and then what is this? Vy is the square root of 3 over 2 times V0, because it's sine. So V0 times sine 60 degrees would be V0 times the square root of 3 over 2. Do you understand? Now after separating, you find the acceleration and draw the graph. After separating, you just find the acceleration and draw the graph. Remember well, okay? Separate, find the acceleration on the x-axis and draw the x-axis graph. Then separate, find the acceleration on the y-axis and draw the y-axis graph, okay? All right, let's see. It's good to split it like this and do it. It's called the x-axis, so it's x-axis motion. This is called y-axis motion. Then, on the x-axis, the projectile does not have acceleration, right? So the acceleration is 0. Then how does the vt graph look? This is uniform motion with 1/2 times v0, right? Uniform motion. So if this is 0, what happens to the st graph? This becomes linear. You're a bit practiced with that now, right? Next, let's look at the y-axis. There is acceleration on the y-axis. It's negative 9.8, right? Like this. Do you understand? Then let's consider an arbitrary t0. What happens to the speed at t0? It becomes 0 on the y-axis. So what was the initial speed? The initial speed on the vt graph was the square root of 3 over 2 times v0, but here the slope downwards is linear. If it's 0th order, then it's first order, right? Then how does the st graph look? The st graph starts from here since we are ignoring the initial height of the projectile, goes up to the peak height, and at t0 it comes down like this. It reaches its peak and begins to descend at time t0. Okay? This is how both graphs are drawn. Got it? Since we've drawn both graphs, we can now solve the problem. Look. What we added here is, as we solved it before, this. What is this? This is delta Vy. Do you understand? At time t0, then how do you calculate delta Vy? Delta Vy is negative 9.8 times t0, right? Then this height is negative 9.8 times t0, right? Do you understand? It decreases by this much. And then what did we say about this area? Let's call it delta Sy. You need to interpret it this way to solve the graph, right? Similarly, drawing this graph is not the end. You need to interpret it simultaneously, right? Then this would also be t0, like this. Do you understand? To0. All here is t0. Then what does this area represent here? This area is called delta S sub x. Here the height is delta Sx. Now let's solve the problem. What is shown is 280 meters on the x-axis. Then for delta Sx, looking at this area, how is the area of the rectangle? 1/2 times v0 times t0. What is this value? It's given as 280 meters. Now, since we have two unknowns, we need one more equation, right? So what's that other equation? This is the same as this height. Do you understand? This is equal to the height, right? Then it's negative 9.8 times t0. What should this value be equal to? Minus square root of 3 over 2 times v0, it should be equal to this amount of change. This delta Vy, do you understand? Then the t0 value will come out. How can t0 be expressed? Let's rearrange the equation in terms of t0. Let's calculate this a bit more neatly with a calculator. Now this t0 comes out to be 0.088 times v0, like this, okay? We can substitute this value here. So, if we substitute, v0 will come out. Right? Then let's substitute it. 280 meters is 1/2 times, then this is v0 times 0.088 times v0, right? Okay, let's do the calculation. When we run the numbers, we find that v0 is 79.8 meters per second, which is nearly 80 meters per second. Since this is a problem I made up myself, the numbers aren't very neat. Now that we have v0, we can find t0 directly if we substitute it back in here. Then it's 79.8 meters per second, so it should be 7 seconds. What is the value of t0? It is 7 seconds. The initial velocity of the shell? You can say this is 80 meters per second. Then the maximum height? When writing the height of the projectile, it's the maximum height. Then it's this area, right? They're asking to find delta Sy, then we can find delta Sy like this. Delta Sy is 1/2. I'll just put v0 value as 80. 1/2 times 80 times square root of 3 over 2 times 7 seconds, right? Then I'll calculate it quickly. So what did delta Sy come out to be? The result is about 242 meters. What is the velocity at that time? That's what they're asking. You need to understand this part well. They want you to find the velocity. Since it's velocity, how is it on the y-axis? The velocity is 0. So for the x-axis, this is the only value we have, right? Therefore, the velocity is 40 meters per second in the x direction. You can write it like this, because it's roughly 79.8 meters per second. So that's the way we'll solve problems like this. This example was a bit challenging, wasn't it? Make sure you review it carefully, all right? We're going to use this exact method for all future problems, including both practice and applied questions. Exam questions will likely be similar, asking for multiple parts, but if you draw this graph, you can solve every part of the problem. So, when you see a problem, what is the very first thing you need to do? Vector decomposition. After vector decomposition, you just find the acceleration acting on the x and y axes, and that's it. Once you have the acceleration, you can draw the graphs, right? Now solve it just like you analyze the 1D motion graphs, but remember to always analyze the x-axis and y-axis graphs simultaneously. Make sure to review it once. If you review it again and grasp the concepts well, you can solve all the problems easily. Let's work hard. Good job.